Okay, so on page 85 it says Theorem 1, the fundamental theorem. That sounds very big. The fundamental theorem of algebra. Oh gosh, I don't know if I want to read all that. If P of x is a polynomial of degree n, where complex coefficients, and the equation has n roots. Okay. This one I already talked about. I don't know why they gave it a pretty big name, the fundamental theorem of algebra. Sounds a little bit too big for it. Basically what they're saying is, do you guys remember what a degree was? It's the term in the polynomial with the highest powers. Is like if this was a polynomial, the degree of this term is 4 plus 1, 5. The degree of the whole polynomial is 5. Anyway, the degree of the polynomial equation tells you how many solutions there are. Remember I already mentioned that. So normally this should have 4 solutions. Unless what happens? There's a double root that counts as 2 solutions. Or a triple root could count as 3. Or a quadruple root could count as 4 or whatever. But there's no quadruple roots in this book. But technically, you know, it could happen. Yeah, so that's rule number 1. If it has a 4th power, it should have 4 roots. So, did you guys notice I'm going to do the next theorem, complex conjugate theorem. You don't have to know the names of these. You do need to know these are true, though. Did you guys notice that whenever we got an answer that was like 4 plus 2i, we also had an answer that was 4 minus 2i? Like, for example, when we did the quadratic formula, you know, you always get like plus or minus in front of the square root. Anyway, so these are called conjugates, and basically when you get an imaginary or complex number, it's as a solution, its conjugate is also a solution. So 4 plus 2i is a root, 4 minus 2i is a root. Similarly, I think this is theorem 3. Yeah. On theorem 3 it says pretty much the same thing, but this time it's with irrational numbers. So if you get like 4 plus square root of 3 as an answer, it'll also have 4 minus square root of 3 as an answer. Okay, so if you know one of them's true, the other's going to be true. Okay, theorem 4 says if a polynomial of odd degree with real coefficients, if it has real coefficients, then the equation equal to 0 has at least one real root. Do you guys remember what we knew about the graphs of odd degrees? 3, 1, 5. They go from down to up or up to down. So that means they're going to have to cross through the x-axis at one point, right? Which means they're going to have at least one real root. Okay, because it's going to cross the x-axis at one point. Where it hits the x-axis, that's where the function value is equal to 0. It's also called the zeros of the function. So if it has to hit the x-axis at least once, it has to have at least one real root. If it were floaty, like this, it would have one real root, and then since these don't touch, it would have 2 imaginary roots. Because cubic functions have to have at least three roots. Boom. Oh gosh, the last one's a mess. I kind of forgot about that one. Theorem 5 for the equation, blah, 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 blah. This is kind of a little bit important. So it says for the equation a sub n x to the n. So n would stand for like which term it is. Like the degree of the polynomial. So if it was like, if it was a fifth degree polynomial, it'd be some constant times x to the fifth plus some constant times x to the fourth. So these little a sub 5s, what I'm telling you is, it just represents the number in front. You guys remember what the number in front of the x is called? Number in front of the term? Somebody say it? Coefficient, yeah. So these little A5s represent the coefficients. Okay, the 5 doesn't do anything down here. It's just saying like the fifth one of these or whatever. It's just a way of counting the different ones. These 5s do something and this 4 does something, but yeah. It's kind of like, you guys remember the formula, like the slope formula or whatever, had little 2's and 1's. Those little 2's and 1's don't do anything. They're just saying, what's the first x? Oh, I did it backwards, didn't it? Second x, that don't really do anything. Okay, anyways, so they are saying that the sum of the roots is always the opposite of the second coefficient over the opposite of the first coefficient. I have no idea how they figured this out, by the way. I've never seen a proof for this, so I don't know where they got this from. So, what are roots? Let's break this down. They said the sum of the roots is equal to this. What does sum mean? If you add them together, you answer to addition. What are roots? They're the solutions when you set the equation equal to 0. They're also called the zeros of the function. They also happen to be the x-intercepts. So all these times when we're solving these equations, we keep setting equal to 0. Roots is one way of calling them. I think we call them zeros of the function, maybe more at the beginning. This book likes the word roots a lot. Anyway, so if this were a fifth degree polynomial, it could have 5 roots. And if you add them all together, let's say I knew this was like 4 and this was like 6. The sum of those roots just happens to be negative 4 over 6. Or negative 2/3. No idea how they figured that out. They're just saying it's true. I believe them. Okay? We're going to kind of need that a little bit later. But anyway, it says the product of the roots. What does a sub 0 stand for in that polynomial? You see it where they wrote a sub 0 on the end up there? And see how there's no x after it? So they're basically saying that's like the constant in a polynomial, like the last number. It's like the number that we're using in the rational root theorem. Anyway, they're saying the product of the roots, if n is even, n stands for the degree of the polynomial, so it's like the second degree, fourth degree. If it's an even degree, then the product of the roots, in this case it would be 7 over 6. If you multiplied all the answers together, you should get 7 over 6. Unless the product of the roots is odd, which actually, if the degree is odd, which in this case it is, it would actually be negative 7 over 6 if you have an odd degree. That kind of halfway makes sense. Probably have to do a problem for it to make sense, what they're talking about a little bit more. Okay, here's something, I'm pretty sure I put one of these things on the test, so might take a note or something. It's written on page 87 in red. Doesn't show up very well, but all right. What this is for is if you have a quadratic equation, how many roots would that be? 2. If you have a quadratic equation, you can write an equation if you know the 2 roots by plugging in the sum of the roots here and the product of the roots here. So their example was, let's say, 2 plus 3i is a root. 2 plus 3i is a root, what else is a root? Okay, what is an equation that has these 2 as roots? Yeah, so if you do the sum, what does sum mean? Add. What do these 2 add up to? 4. 2 plus 2 is 4. 3i plus negative 3i is 0. So it's just 4. So it would be x squared minus 4x plus, what is the product of the roots? That would be more like a FOIL problem. Since they're conjugates, you don't have to do the whole FOIL, you can just do first and last. 2 times 2 is 4. 3i times minus 3i is minus 9i squared. Remember that makes a negative 1, so this becomes negative 9 times negative 1 plus 9. So 4 plus 9 is 13. So anyway, that gives you a... If they're simpler roots, like let's say the roots are 2 and negative 4, for example. You could use that formula, and actually it would be really easy to use the formula. But if you forgot it, if 2 is a root, then I know x minus 2 is a factor, and if negative 4 is a root, I know x plus 4 is a factor. And I could just, this is an equation, and I can FOIL it together. This is an equation with 2 and negative 4 as roots. I just FOILed that. You guys see how I got from here to here? Elena? You see how I got from here to here?
Yeah.
And how I got from here to here?
Opposite.
Yeah. So normally we solve the equations, right? We factor the equation and we say x is 2 and negative 4. They're saying the solutions are 2 and negative 4, so what's the equation? So I just work backwards. X minus 2 times x plus 4 equals 0 is the equation. FOIL that together to put it in standard form. But yeah, this, if you can remember that, that's probably easier a little bit. And yeah, you could use this with this trick with imaginary numbers. It's a lot more complicated than this is, though. You'd have to do, and actually I'll keep that. You'd have to do x minus that as a root and x minus this as another root, and then do a FOIL thing, and it's a mess. You don't want to do it. All right. Okay, page 89. Tell whether the statements in 1 through 8 are true or false. Justify your answer. All equations mentioned have real coefficients. Yeah. they're basically the theorems they talked about only work with real coefficients, like no imaginary coefficients. Yeah, anyways. Number 1, some cubic equations have no real roots. True or false? You guys remember the theorem we talked about, the one with that one? Is it possible for a cubic equation not to have a real root? It's false. Remember me coming over here and being like, it's got to go through the x-axis at some point because it goes from down to up. Okay, it is false. You have to have at least one real root. Which theorem stated that basically? Odd degrees have to have at least one real root. Which theorem was that? Theorem 4. So they said we have to give a reason, so I'll abbreviate theorem 4. I'm going to help you guys with all the 1 through 8 part. Okay, number 2, every polynomial equation has at least one real root. This one's harder. Does every equation have at least one real root? If this W, or here's this, does this have a real root? No, it's not going through the x-axis at all. So no, not every equation does. So what they did for this one is they made a counterexample. So they said, what if the real roots were like, or sorry, the roots were plus or minus I. Then you'd get an equation. What's the sum of these roots? What's the product of these roots? Minus I squared minus negative 1 plus 1. So this equation, x squared plus 1, has no real roots. It's that. If we solve this for x, we get plus or minus I. So this is a counterexample. Okay, number 3, the roots of a certain quartic equation. Do you guys know what quartic was? Degree of 4. One of, anyway, towards the bottom over there. Are plus or minus a half, 0, and 1 plus I. Is that possible? Right. If 1 plus I is a root, what else is a root? 1 minus I. So that would be 5 roots. So this kind of breaks. So we knew it had to have 5 roots based on the, what they call it, the imaginary, or the complex conjugates theorem. And it can't have 5 roots based on the ultimate algebra theorem, whatever they call it, fundamental theorem of algebra. So they kind of used theorem 2 and theorem 1. What did the book say? I can't find the answer. Hold on. I have no idea where to put the answer. Oh, they didn't even say it. They just said false because 1 minus I must also be a root. They didn't go into the whole explanation. they didn't say and they probably should have said and a fourth degree cannot have 5 roots. They wrote that wrong. Fourth degree polynomial cannot have 5 roots. Number 4, the roots of a certain fifth degree equation are -3, 4, 1 minus square root of 2, and plus or minus I. This is the same problem. If 1 minus square root of 2 is a root, what else is a root? 1 plus square root of 2. So we have 1, 2, 3, 4, 5, 6, and that can't be a fifth degree, so it's the same as the last problem, I guess. I don't know why they did that twice. Well, okay, anyway, false. 1 plus square root of 2 must also be a root. I don't know why the AC is always on in the morning and the afternoon. It almost never turns on. What is up with that? Number 5. It is possible for the graph of a cubic function to be tangent to the x-axis at x equals -2, 1, and 6. Alright, this goes back to geometry. What does the word tangent mean? No idea, no recollection. Something like that, yeah. So this line is tangent to the circle. It touches at one point, just barely brushes up, touches exactly one point, and just keeps on going by. So if a graph is tangent at like, what did it say, -2, 1, 6, might look something like this. So what kind of roots are these? Double roots, double roots, double roots. So this has to have a degree of at least what? 6, 2, 2, 2. Double roots count as 2. This has to have at least a degree of 6, not a degree of, what did it say? Cubic, 3, not a degree of 3. So it's another false. I wonder if we're going to get any truths. They just put, their explanations aren't very thorough. They just put three double roots. Imply a degree of at least 6. Number 6. No polynomial equation can have an odd number of imaginary roots. No polynomial equation can have an odd number of imaginary roots. So, if like 2i is a root, what else is a root? If 0 plus 2i is a root, what else is a root? 0 minus 2i, or -2i. So is it possible to have an odd number of imaginary roots? No. So their statement, no polynomial can have an odd number of imaginary roots, is true, and basically that's just another way of saying theorem 2. They have to come in pairs. I know these are hard, that's why I'm helping you guys. Suppose p of x is a polynomial with rational coefficients. So it's like a normal polynomial. And b is rational, but square root of b is irrational. If square root of b is a root of the equation, then negative square root of b is also a root. Okay, there's kind of a lot of fluff on that one. So basically they're kind of saying if this is a root of the equation, this is also a root of the equation. Is that true? Yes. Which theorem said that was true? No. 2 was for imaginaries, and 3 was for irrationals. They kind of say the same thing, but one is imaginary, the other is just irrational, like square root answers. So it's actually theorem 3. Number 8, if a plus bi is a root of the equation, so some complex number a plus bi is a root, then the equation must have an even number of roots. Is that true? Well, so for example, like if 2, let me make the number small. If 1 plus I is a root, what's another root? Okay, does it have to be an even number of roots? Well, we saw some yesterday that were like, had a couple imaginary, but also like one real root or something, right? So no, it doesn't have to have an even number of roots. It could have an odd number. So they just gave a counterexample. If we it'd be hard to do, wouldn't it? So if I use that formula thing, to make a polynomial out of these two guys that has a quadratic polynomial that has these as roots, the sum of those would be 2. The product of those is 1 minus I squared, so it's 1 plus 1. Okay. These two are answers to this equation if you set it equals 0. And if I just multiply that by like x minus 2, that would give me a quadratic equation with all 3 of those as roots. So that's just an example. I'll just leave it like that. That's an example of a equation that has an odd number of roots with an imaginary root. How should I say this? I'm not going to multiply it out. Too much time. Write a little book here. Jeez. Alright. Forgot to zoom out. Let's go. Alright. Number 9 says find the sum and the product of the roots. So that was theorem 5. if you look at theorem 5 on the previous page, it says the sum of the roots is basically the opposite of the second coefficient over the first coefficient. Okay, that's what that means. It's a complicated way of saying that. So, what is the second coefficient on number 9? -3. It could be like 0 if they skipped a term in the order. It might be 0. So anyway, it's the opposite of -3 over what's the first coefficient on number 9? 4. So -3/4 is 3/4. I don't know what the roots are. I don't know what the solutions to that equation are, but whatever they are, they should add up to 3/4. That's what we're saying. It's just a trick they figured out. I have no idea how they figured it out. And then it says, find the product of the roots. So if we go back and look at the product of the roots, it says, if n is even. So if the degree is even, on number 9, is the degree even or odd? Even, because it's a second degree polynomial. We're supposed to just do, basically, this is the last coefficient over the first coefficient. Kind of like what we did yesterday in the rational root theorem. So what is the last coefficient? 6. And what's the first coefficient? What's the 6 over 4 equal? Um, 11. So same thing. By the way, if it was an odd degree, you do the same thing, but you just put a negative on it if the degree is odd. Alright, number 11, so we need the sum. So it's this thing right here, is the opposite of the second coefficient over the first coefficient. What's the second coefficient on number 11? 5. So it's -5 over first coefficient 3. And then the product of the roots is the degree on number 11 odd or even? Odd. So we need to use this version. It's opposite the last coefficient over the first coefficient. What's the last coefficient? It's -2. What's the first coefficient? 3. So it's -2/3 or 2/3. Oh gosh. Why don't you guys try 10 and 12? You've got like a minute. Go. Minute and a half. Possibly less. I lied. Alright, this won't be due tomorrow, obviously, but we are not just going to work on this tomorrow because we're almost done, basically. There's not a lot to this lesson.